Okay, empirical trigonometry, using data to find and prove useful approximations. We're going to prove all of these. A few weeks ago, we used graphs to find a useful limit. This week, we will continue using data based on trigonometric functions like sine, cosine, arcsine to find useful approximation. Data allows us to see relationships that otherwise would be hard to find. So we'll use data to leads to discoveries, which ultimately leads to a proof. Obviously, we like to see the proofs, but it all starts with discovery and data. So we know these relationships. The 1 minus cosine over theta squared we proved a few weeks ago. So these are useful, but a constant theme in mathematics is, can we generalize these results? Can we go further? So we're going to try to find n, m, and k such that these relationships approach the limits, useful limits like a, b, and c, where a, b, and c are non-trivial constants. If these limits exist, they can be useful for two reasons. They could help us in estimating errors, but they could also help us find better approximations. So exercise 1. This is the main exercise here of this. We're going to compute data for sine and 1 minus cosine for a bunch of values, having theta each time, and we're going to use that data to figure out the order of the process. Those are the n, m, and k, and then the limits, which are a, b, and c. So let's go to the spreadsheet and do this. See if we can figure out the relationships. Okay, now these calculations we've done before. We start at 60, that's pi over 3 in radians. And we know the cosine and the sine values for those. We're going to compute the difference between theta and sine. And then we're going to divide the angle by 2, and we're going to use our half-angle formulas for cosine and sine, which we've used many times before. You should know these. This one's sine divided by 2 cosine. And bring those calculations down. And then we're going to see how quickly theta minus sine declines. And it's 1 over 8. In other words, each one is 1/8 as big as the previous one. That means it's a third order process. And we're going to divide the residual by theta to the cubed. And that should be a constant when we divide. So let's take the reciprocal and see if we can recognize the constant. It's 1/6. It's not exactly 1/6, but it's very close, about as well as you can do with this kind of data analysis. You lose a lot of digits doing this, by the way. Okay, now let's do arcsine. It's basically the same calculation because we're just going to call x is sine and arcsine is theta, and arcsine minus x is the same as theta minus sine of theta. So that process is declining by a factor of 8 each time, so it's a third order process. So we know that we should divide by x to the third power. And that should approach a constant, and it does. And maybe not too surprisingly, it's the same constant as before. It's 1/6. About the same accuracy, not a big surprise there. Okay, let's look at cosine now. Most of these calculations we've already done. We're just going to do the 1 minus cosine. The way you calculate 1 minus cosine, you don't want to do 1 and then subtract the cosine value. You want to do sine squared and divide by 1 plus cosine. You'll get a better value. It's critical here because you lose digits in this process. The residual is 0.5 times theta squared. And we're going to subtract the 1 minus cosine. We'll bring that calculation down. And then we'll look at the order of the process by seeing how quickly it declines, and it's 1/16. So that means it's a fourth order process. That means we divide the residual by theta to the fourth power. It's not a big surprise that it's fourth order because we've already done the second order term. The next one would be the fourth order term. So the ratio is the constant we're trying to find. And let's take the reciprocal of that number to see if we can recognize it. It looks like it's 24. Not exactly, but pretty close. It's about as well as you can get with this sort of data analysis. So this answers the question. So we found empirically these three limits. So now the question is, can we prove them? It raises some questions. Are these true? If so, can we prove them? If we can't prove them, how would we answer the first question? So yeah, basically the first question is silly. We need to prove them. And the third question is, how can we use these limits in our estimates? Well, we will definitely be able to use them if we can prove them. They'll be very useful. So the first proof, theta minus sine theta over theta cubed, limit equals 1/6. This is the hard one. So we're going to use a trigonometric identity for sine of 3 theta that you can derive on your own. Very simple to prove. It's 3 sine theta minus 4 sine theta cubed. Now we're going to multiply by minus 1, and then we're going to add 3 theta to each side. And then when we get this relationship 2, we'll divide by 27 theta cubed. That's because the left-hand side will be a limit in the form of 3 theta. So we'll take the limits as theta goes to 0, and we'll get L3 is equal to 1/9 L3 plus, and the last limit is 4/20/27. So L3 is equal to 1/6. But that doesn't actually prove that the limit exists. It just shows that if it exists, then it's equal to 1/6. We need to show that the limit is bounded. If we can show that the limit is bounded, then what we can do is we can use the recursion relationship that we derived to show that the bound can be made smaller and smaller until the only value that exists is 1/6. So now we're going to try to find a bound on the limit. So we'll use this diagram. It's an arc of a circle. And there's an arc of a circle, and there's a triangle that we're subtracting from the arc to make that blue lens-like shape. And the blue area is 1/2 2 theta minus 1/2 sine of 2 theta. You can verify that for yourself. And then there's an orange rectangle, and that's easy to see as 2 sine theta times 1 minus cosine theta. And the blue area sits entirely within the rectangle. So that gives us an inequality. And if we divide by 4 theta cubed and take limits, we can find that L3, which is the limit we're trying to find, is bounded above and below by 0 and 1/4. So we'll do a little exercise. We'll calculate these bounds as using the recursion relationship that we derived, starting with 0 and 1/4. And we'll just calculate this sequence really quickly to see what it looks like. So we're going to go back to the spreadsheet. This is a real simple calculation. C is 4/27. L is 0. L0 is 0. U0 is 1/4. 4. And then the difference is 1/4. And then the next, we'll use the recursion relationship, the constant plus 1/9 of the previous value, to calculate the new bounds. So notice the new bounds are much tighter. In fact, we can calculate the ratio of the difference, and that's always going to be 1/9, for obvious reasons. And that means that every step, the bounds are giving you about 1 digit. And so it fairly quickly converges to 1/6. Okay. All right. With that proof out of the way, we'll do arcsine. And arcsine, we're going to use basically the same result, the same limit, but we're just going to plug in the relationship that theta is equal to arcsine of x in there. And then we'll pull out an x cubed over arcsine cubed of x, and we'll show that that's equal to 1. So the ratio, so the arcsine of x approach the same limit. Okay, now cosine. This one is also fairly easy. We're going to use the same theta minus sine theta over theta cubed result again. So we'll start off with this relationship. Cosine 2 theta minus 1 is equal to minus 2 sine squared theta. We'll add 2 theta squared to each side. The right hand side will nicely factor. But the first step, we're going to divide by 16 theta to the fourth. And then we'll factor the right hand side. And this is where we're going to use that cubic relationship that we proved, that limit's equal to 1/6. And the whole limit is 1/24. Okay, time to close the spreadsheet. Thank you.